Hello. So let's start with the first section of the part on tabular reinforcement learning. So what you have in the Sutton and Bartow book, which is Bandits. So we'll talk about Bandits. So it's a sub-case of reinforcement learning that will allow us to see quite a lot of concepts which will be very useful for the rest of the course. In terms of applications, it's not very important, but we will see really the basic things that you need to know in RL. So as we have seen in the introduction, the basic concept in reinforcement learning is trial and error. So you try an action and you get a feedback that tells you if that action is good or not. So that's called evaluative feedback. That means that the feedback that you get, the thing that is returned by the system, depends on the action that you take. And that's the main difference with supervised learning, which is called also instructive feedback, because it doesn't depend on the prediction. So if you have a network learning a classification task, it makes a prediction and then it's compared to the ground truth. But the ground truth doesn't depend at all on the prediction. So that's the first distinction we can make, that RL is called evaluative feedback. Second distinction we can make in the type of learning that we can do in this course is associative versus non-associative. So in non-associative learning, you just have actions. It means you are randomly trying actions, it gives some reward or not, and you try to learn from that. It doesn't depend on the state of the system or on the history, and that's what bandits are. What we are going to see next time, and that's the general RL framework or Markov decision processes, where a state will influence which kind of reward is obtained after doing a particular action. So that's another distinction. So here we stay in the non-associative learning case, where we only have actions and we will ignore states for the moment. So what we call the n-armed bandit or multi-armed bandit is a non-associative evaluative feedback procedure. So the bandit is like what is described on this figure. Imagine you are in a casino and you have a row of slot machines. You can act on each of these machines individually. That would be one action. And you get a reward, which is I gain some money or not every time I press one of the levers. So what you have to choose is which action to perform. That means which slot machine should I choose to get the most reward. So let's say that these machines are all different. On average, they will give different amounts of money. And we want to find, through trial and error, which of these machines is the best, so that if I press the lever many times one after each other, on average I will win more money than if I pick another one. Alright, so as you can see, it has not many applications, but we are going to see how to solve this problem, and that will give us a lot of insight for the most complex RL setup. So let's start by being a bit more formal on our problem. So let's say that we have the choice between n different actions that we will call A1, A2 until An. And at each trial, so every time you pick an action, you will get a reward at time t, which is drawn from some probability distribution that you note R of the action. So the reward probability of the action. So the probability could be anything. It doesn't have to be uniform or normal. It could be anything. Just it has an expected value, which is the mean reward that you get with this action. So here you have an example of a bandit with 10 different actions, and the bars represent the mean reward that you can obtain if you select that action, and the line perpendicular to this bar is the variance, or the standard deviation of the reward that you get. That means among all these actions, there is one that is better than the others, that is optimal action. But it doesn't mean that you will always get that amount of reward. You may get very low reward or very high, depending on chance. And it can happen that if you pick this action and you're unlucky, it's in the lower half of the distribution, this action could in fact give you a much higher reward. But what's going to matter is just the expectation, so the mean reward that you obtain when you get that action. This mean reward is called the true value of the action. So we'll come back next time on what value means and why we have this notation. But we are going to note that Q star, that's the optimal value, the true Q value of an action. And it's a mathematical expectation of the reward distribution for the action. So what we search is that, and then if we have this value for all the actions, we are going to pick the action which is highest in terms of true value. So you already see that we ignore the variance of these reward distributions. That's something we will do all along in that course in reinforcement learning. We are considering that we can try each action an infinity of times, and so what's going to matter is just the average. The variance, we omit it, except later in the course we will talk about distributional RL, where you try to learn the variance too. But in the first part of this course, we only care about expectations, about mean values. So the problem is, how can I learn these values with trial and error? It means just sampling. I try an action, I get some reward, and then how do I choose the next action? The problem in RL is that these reward distributions are unknown. You just want to try to sample from the world in order to estimate what these values are going to be. So the true value of an action, so the real expected value of the reward distribution, is noted like that. It's often called utility also, so the utility of an action, especially in economics or in decision making. So our problem is that we don't know it and we want to estimate it. That's why in the last lecture you had a section on estimators, so sampling, because we are going to try the different actions many times, and every time we sample we get a different value from the reward, because it's probabilistic. And from these samples we are going to want to estimate the expected value. That means over time, and in RL time is really an essential component, you cannot skip it. You are going to do the tries one after each other. You are going to build estimates of the true value. So we know this estimate Qt because time will increase every time you do an action, and you want your estimates Qt to converge towards the true value, so to be an unbiased estimator of the true value of the action. And that's the goal. So you see that at the beginning, when you don't have many samples, because of the central limit theorem, your estimates will be wrong. But the more samples you take, the more your estimate should be close to the true value. That's really an important concept to get first, that everything we will do in RL is just estimating distributions. And these estimates will get better the more samples you take. Let's talk again about sampling. So as we have seen, if you want to estimate the expected value of a distribution and you get samples, you can simply use the sampling average or the mean of the sample that you take. So what we are going to do is take n different samples, try the action n times, get the reward that we get every time, store it, and then make the average of that. So here this notation is a bit weird. So the sum over time, so the different tries that we make, of the reward received at time t, given that we select the action A at time t. So this bar is just a form of conditional probability, if you want. So RT are the samples, and R is the distribution. So the only thing we need to know to estimate the value of an action is to get to remember which rewards we have obtained every time we chose that action. The first time we got R1, then R2, and then RT. And the estimated value of an action at time t, or at play t, for example this reward, is the average of all the rewards which you got before while doing this action. The sum of all the rewards dividing by the number of times you selected that action. And of course that should converge at the limit when you take an infinity of samples to the true value of that action. So this is really basic, but actually it has a problem. It's not very practical for us, because that means that for all actions which are available in your problem, you need to remember all the rewards that you got since the beginning of learning to every time change your estimate Q. That means if you have thousands of rewards taken after an action and thousands of actions, you need to remember millions of values to compute every time this mean. That's not very good. And the way we are going to do it is in an online manner or incremental manner, which is just by splitting this sum. So let's say that you are at time t plus 1. So you have already done t actions A, and you try it another time. So what is going to be the new Q value, the new estimate, if you know the previous one at time t? So it's 1 on t plus 1, the number of actions sum from 1 to t plus 1 of the rewards, and you just separate the last reward from the previous sum. And this previous sum, you see it from here, that's t times the previous estimate qt. So just replace this sum by that. And with a bit of manipulations, it becomes the reward you just got plus t plus 1, the previous estimate, minus the estimate. So if you change that a little bit, see that you have a t plus 1 here and a t plus 1 here, they're going to cancel. So that means you can get this previous estimate at time t out of the loop, and your new estimate, qt plus 1, is going to be equal to the old estimate qt plus 1 on t plus 1, number of samples, the difference between the reward that you just got at time t plus 1 and your previous estimation. It's just basic manipulations of this formula, something very easy to obtain. The advantage is that you don't need to remember all the rewards which you got in the past. Just need to know the one you get just now and your previous estimate. And this formula is exact, so that's exactly the same as remembering all these rewards and making the mean. Now, this way of estimating the mean has a problem, that it only works when the reward distribution is stationary. It means when the statistics of that distribution, its mean or variance, do not change over time. If you have a problem which is non-stationary, which changes over time, that's going to be the case in RL, the 1 on t plus 1 term decreases actually, every time you take an action. So very soon, this update here will be multiplied by 0, something very close to 0, and your updates are not going to change a lot, your estimates. So here you have a figure. Let's say the red line is a true Q value, and after 20 trials, it changes and gets a new value. Here you have the samples that you get, so they are around the true Q value, but a bit distributed. And then suddenly, the reward that you get all get higher. Your estimation with the online formula we just saw is going to quickly track the true Q value. So very soon after, let's say 10 samples, the mean of these 10 will be around the true Q value. But then when the mean changes, then it will take a very long time to come close to the new value for the true Q value. So that's because this 1 on t+1 term is very small when you have made too many tries. So the updates that you have made, the difference between two successive values, will be very small. So it's going to be very slow. So one way to solve this problem is to replace this factor 1 on t+1 by a fixed parameter which doesn't depend on time, which will be called the learning rate as in machine learning, or the step size. We will note that alpha, and that's a fixed value that doesn't change over time. So your learning rule becomes that your new estimate for the Q value of an action is going to be equal to the old one plus alpha, this parameter, times the difference between the reward that you just got and your previous estimate. If you manipulate this a bit, it takes this form. It's 1 minus alpha, the previous estimate, plus alpha, the reward. This kind of balance between the old estimate and the real reward that you get. This way of computing with a fixed step size is called a moving average or sliding average, or an exponentially moving average, different terms. And that's ways of estimating the mean of a distribution, or the expected value, as if you use a small window of the past history. So if you're here, for example, you are going to use a window of the past which decreases exponentially when you go backwards, because every time you will multiply your estimate with 1 minus alpha. So 2 steps away it will be 1 minus alpha squared, and then power of 3, and so on. That's why it's called exponential. It goes to 0 because 1 minus alpha is smaller than 1. But the advantage of this method is not exact, but it can adapt quite quickly to a non-stationary problem. So here that's the orange line. It quickly tracks the mean, so it's quite good. And when the distribution changes, it will be able to adapt to the new distribution, because quite quickly it forgets the examples which are too far away in the past. So it becomes blind to them and can change its value much faster than the true exact average. It will just increase very slowly. So in practice, that's what we are going to use, always with a fixed learning rate or step size. So a new estimate will be equal to the previous one plus a small part, it's always smaller than 1, of the difference between the reward that you receive and your current estimate. So to summarize, this moving average can adapt very fast to changes in the reward distribution, so it's fine for this kind of non-stationary problem. It's not exact, and choosing the right value of alpha is quite tricky, because if you set it too high, then it can be very sensible to noise. And it's not exact, so it's not exactly an estimate of the mean or expected value of your distribution. It's not far away from it, but it's not exact. What's important to remember is this kind of update of an estimate that we will use all the time in that course, but that you use also in machine learning, that you will change an estimate, get a new value for the estimate, the function of the previous estimate, plus a little part of the difference between a target value, what it should be, and your previous estimate. So here, what your estimate should be is on average the reward. So the target is the reward. And when your estimate is different from the reward, it means you're making a mistake, and you should change your estimate to fix that mistake. That's a kind of learning rule or update rule that will be used all the time. And target minus previous estimate is called the prediction error. Qt predicted that I would get a reward of 1, but I got a reward of 2. So I have a prediction error of 2 minus 1, And so that means I should increase my Q value, my estimate, to be closer from 2. That's what it's going to do.